The cosmos inside an onion skin.
Chapter 3: The Labyrinth of Modern Physics and Its Enigmas.
On any beach, when you grab a handful of sand and let it fall to the wind, you will see that it is made of a very large number of grains. Now imagine the number of grains of sand that exist on this entire beach.
If we consider all the beaches and deserts in the world, that's a lot of grains of sand, isn't it?
But the total number of grains of sand on Earth is still smaller than the number of stars that exist in the universe.
In our galaxy, there are something between 100 and 400 billion stars.
And if we look across the entire universe, we find that there are 1 to 2 trillion galaxies.
But these tiny grains of sand are deeply connected with all the stars in the universe.
Each grain is made of billions of silicon atoms, and these atoms did not exist in the early universe.
The atoms on this beach, as well as the atoms in my own body, were forged in the cores of stars.
In the early universe, there were only very simple atoms, mostly hydrogen, spreading through immense cosmic clouds. These vast clouds of hydrogen slowly collapsed under gravity, forming gigantic blue stars.
These stars shine because they fuse hydrogen into helium, releasing energy as light and heat.
But massive blue stars live briefly. They burn through their fuel quickly, collapse, and explode.
These explosions created the heavier elements, the grains of sand, the Earth, and even the atoms in our sun. Everything around me, even this water, was created in stars that exploded billions of years ago. But there is something deeper that connects the grains of sand and the water molecules to the stars, something beyond their vast numbers.
Grains of sand, water molecules, and even stellar plasma, all of them are made of atoms, contain a small central nucleus made of protons and neutrons, with electrons orbiting the nucleus.
Electrons are extremely light, and almost all the mass of an atom lies in its nucleus, shared nearly equally between protons and neutrons. And this ocean remains here because the mass of its protons and neutrons is attracted by the mass of the entire Earth. But what are these grains of sand, really? What are silicon atoms? What are water molecules? To answer these questions, we need to look at science from a historical perspective.
Holes in the scientific wall.
When we study science at school, in primary education, secondary school, and even in university courses, science, especially physics, is often presented as something finished, complete, and almost perfect. We are given the impression that science already understands how the universe works, that all the great questions have been answered, and that only minor things remain to be detailed. In some areas, like mathematics, this is mostly true. Only a few deep problems remain unsolved. In physics, however, some things remain unclear, and many fundamental questions remain open. As the wall is built, some pieces are missing. To avoid stopping the process, holes and gaps are left. This wall began to be built 400 years ago with Galileo Galilei, the father of modern science. Over the centuries, this wall has grown taller, but it was never built with perfectly fitting pieces. Many stones are missing, and very often physicists do not fully understand all the deep details. As a result, modern physics offers a very good overall picture of how the universe behaves. But at the same time, it contains many enigmas, not only at the edges, but at its very foundations.
Enigmas of modern physics.
Despite gravity being easy to observe, the true origin of gravity remains a great mystery to this day. 3 centuries ago, Isaac Newton empirically obtained the law of gravitational force.
The force that makes an apple fall is the same force that keeps the moon near the Earth.
This gravitational force arises between two bodies with mass, separated by a certain distance. If the mass doubles, the force also doubles. And if a mass is zero, the force disappears. Thus, the gravitational force is proportional to the product of the two masses. If the distance between the masses doubles, the force is divided by 4.
And so the gravitational force is inversely proportional to the square of the distance.
Since this force is extremely weak for small masses, a proportionality factor is required. I called this proportionality factor the gravitational constant, given by the letter G. The G value can only be measured experimentally and cannot be derived theoretically. And so, my formula for gravity is provisional, as there are several things I do not yet understand. When we truly understand how gravity works, the constant G will disappear from the equation. And in its place will appear the true roots of gravity, which actually generate the gravitational force. Newton's empirical equation works, but even today, we still don't know why matter attracts matter. About a century ago, our understanding of gravity was completely redefined by Albert Einstein. Massive bodies bend space-time, and smaller objects simply follow these curved paths. But in Einstein's description of gravity, there is no force pulling objects together. However, even Einstein's model has limitations. If a small body begins with zero velocity, in this situation, space-time curvature alone cannot fully explain why the smaller body begins to fall. Without any interaction, it will not start to move. So Newton's force is still required. So while Newton's model does not explain everything, Einstein's model also has its own problems. And neither model can tell us what the constant G really is, or where it comes from. This mystery about the true nature of gravity and the meaning of G is just one example.
Until today, modern physics faces several unresolved enigmas.
In cosmology, the early universe should have produced matter and antimatter in equal amounts. But today, we only observe matter. The antimatter is gone. Where did it go? Galaxies form elegant spiral shapes. At their centers, we always find supermassive black holes. But we don't know how these black holes arise or what their role is in the galaxy's formation. Galaxies also rotate too fast, meaning that it contains some kind of dark matter. But to this day, we still do not know what dark matter is and what it is made of. Throughout this series, these enigmas will be examined in detail. And for each enigma, a possible and valid solution will be presented.
Tree of scientific knowledge.
The word philosopher comes from the Greek philosophia, meaning a friend of knowledge. In its origins, science was created within philosophy and was not divided into disciplines. In ancient Greece, philosophers sought to understand the universe by seeing the world as a whole. They asked questions about nature, numbers, motion, life, ethics, and the cosmos itself. Plato was a Greek philosopher who explored abstraction and the existence of ideal forms. Thales of Miletus searched for a single natural principle behind all things.
Pythagoras believed that reality was structured by numbers. Aristotle developed logic, classification, and the idea of causality.
However, Greek philosophers remained in the realm of ideas and rarely tested their theories experimentally. It was only in the 17th century that Galileo introduced the experimental scientific method.
This new approach structured science and laid the foundation for the tree of scientific knowledge. At the base of this tree, philosophy remained as the root that sustains the entire scientific knowledge structure. Over time, philosophy gradually moved away from mathematics and the exact sciences, and modern philosophers began to address more human and metaphysical questions. Climbing up the tree, we find mathematics, which underpins all the exact sciences. Mathematics provides the foundation for physics, which seeks the fundamental laws of nature. From physics emerges chemistry, which divides into inorganic and organic branches. Organic chemistry leads to biology, from which veterinary science and medicine emerge. Inorganic chemistry gives rise to material science, industrial processes, and engineering. Together, these fields form one side of the tree of science, known as the exact sciences. On the other side of the tree are the human sciences. Philosophy remains a common root, but these fields rely less on mathematics. This includes areas such as language, history, sociology, psychology, and politics. This structure shows that science is not a random collection of facts, nor fields defined arbitrarily.
The tree of scientific knowledge is an evolving architecture of ideas that grows continuously.
Challenges of science education.
The advancement of science is only possible through the expansion of the education system. In ancient Greece, schools were created by philosophers, and only a few citizens had access to knowledge. During the Middle Ages, knowledge was held by master craftsmen and passed to their apprentices. At the same time, the church concentrated written knowledge inside monastery libraries. But in these libraries, books were rarely studied and were mostly copied by hand by monks. Over time, these book collections became the seed of the first universities in Europe. With the Industrial Revolution, the need for trained labor grew, and then education became broader, more structured, and increasingly accessible to society. But this new demand for trained people also required new ways of organizing education. Perhaps because of this, the greatest influences on the modern educational system did not come from an educator, but from a famous industrialist named Henry Ford. Ford revolutionized industry by creating large-scale assembly lines for automobile production. The basic idea was simple. Place a chassis on a moving line, and as it advances, add wheels, an engine, and other components. At the end of the line, a complete vehicle emerges every minute. This same industrial logic was adopted until today in both public and private schools. A child who enters school is treated as a blank book, meant to be filled with standardized content. Year after year, a fixed and detailed curriculum dictates which subjects must be learned. Unfortunately, what works for producing cars and TVs does not work for educating people. A century ago, the philosopher Jean Piaget pointed out a fundamental flaw in this approach. Knowledge cannot be delivered fully formed. It must be constructed step by the learner. True understanding comes from rediscovering ideas, not from memorizing finished results.
Unfortunately, Piaget's constructivist model is difficult to apply and was often poorly implemented.
But in some educational cultures, particularly in Japan and China, we see a different balance.
Learning is closely connected to life experience, respect for elders, and all kinds of work. For example, in mathematics, students do not receive the value of pi as a list of digits. They discover the value and meaning of pi using rulers, strings, and circular objects.
This shows that the constructivist model can work without losing sight of clear learning objectives.
Today, we face a new opportunity: the emergence of artificial intelligence as a tool for education. Perhaps this will finally allow us to reconcile structured curricula with constructivist learning. But the basic fact remains: children are not cars, and knowledge must be built, not memorized.
The Labyrinth of Modern Physics.
Imagine the universe as a vast, three-dimensional labyrinth with many levels. This labyrinth has countless corridors, hidden chambers, sealed doors, and secret passages. Scientists do not see the whole structure. They need to explore it step by step. They enter the labyrinth and carefully examine the walls, searching for secret doors. Each new door leads to a new room or corridor, and gradually a map is drawn. From mapped rooms, they estimate the location of hidden spaces and try to find them. This analogy has limits, but it helps to see the connection between scientific models and reality. At the beginning of modern science, starting with Galileo, the labyrinth map was small. There were few explorers and few paths, but over the centuries, the map greatly expanded. Larger teams entered the labyrinth, sharing discoveries and detailing the known regions. Sometimes, a single scientist discovers an entirely new entrance to the labyrinth. And so, the work of one brilliant scientist can change everything that was already known. But because of new entrances to the labyrinth, modern physics now faces a serious problem. Instead of a single unified map of the labyrinth, we now have up to 5 maps of different regions. The problem is that these maps are not linked, and they explore different scales of reality. To better understand this, we need to look at the main labyrinth maps of modern physics. The first map was started by Galileo Galilei and later expanded by René Descartes, Johannes Kepler, and Isaac Newton. This map is known today as classical mechanics. Classical mechanics describes objects at human scales: tools, machines, moons, and planets. It includes the laws of motion, forces, gravitation, fluids, gases, heat, pressure, and energy. In the 19th century, Lord Kelvin looked at the labyrinth and its map and said,
"Physics was almost complete, with only a few small clouds remaining on the horizon."
But everything changed when physicists began to apply Newtonian laws to light. In Newtonian physics, the speed of light should be dependent on the motion of the observer.
The speed of light is very high.
300,000 kilometers per second.
Our interferometer is cross-shaped.
Yeah? One arm is aligned with the Earth's motion.
Earth travels in an elliptical orbit around the sun
at a speed of 30 kilometers per second.
In this arm, the light travels slower.
Yeah. As it moves in the same Earth direction.
On the way back, the light travels faster.
Because it moves opposite to the Earth's motion.
But the time differences do not cancel.
And so, Light's total travel time changes.
On the other arm, light speed is constant.
Oh, because it is perpendicular to the Earth's motion.
So each arm has a different light travel time.
And if we rotate the interferometer, the light wave phases change.
And we see interference patterns on the screen.
However, the Michelson-Morley experiments failed to measure variations in the speed of light, because no interference pattern was ever detected, even after 7 years of measurements. No matter how the Earth moved through space, the measured speed of light was always constant. Solving this enigma, Einstein opened a new door in the labyrinth, where space-time is not constant. Note that in the Newtonian labyrinth, space and time are constant, and there is no speed limit. In Einstein's labyrinth, the speed of light is constant and represents the maximum speed. Thus, we now have two different labyrinth maps, one for low speeds and one for high speeds. Einstein also showed that light follows curved space in the presence of matter. And so, Einstein opened a new access point to the labyrinth, creating the maps of relativity. Another labyrinth door was opened by Max Planck, the quantum mechanics map. Planck was studying hot metal cavities, emitting energy in continuous frequency bands. But when calculating the total emitted energy, all wave frequencies must be added together. But this was like summing numbers between 0 and 1, leading to infinite energy. To avoid this infinite sum, Planck proposed that energy is quantized in packets, or quanta. This is like summing only multiples of 0.1, producing a finite total. But energy quanta mean that, compressing a spring, there is a minimum step of motion.
When I compress this spring, it appears to pass continuously through all possible lengths. But since each length corresponds to a specific energy, and energy has finite values, the spring can only assume a finite number of sizes. This number is so large that the spring size appears to vary continuously. But in fact, it assumes billions upon billions of discrete sizes.
This means that, at the smallest scales of the universe, motion may no longer be continuous. Because if energy has a minimum packet size, space and time themselves become discrete, where the shortest distance is the Planck length, and the shortest time is the Planck time. And so, particles will move in discrete steps, much like pieces on a chessboard. Following the path opened by Planck, scientists like Bohr, Schrödinger, Heisenberg, and Dirac expanded the map of quantum mechanics, which describes the atomic and very small universe. The fourth labyrinth door was opened primarily by new experiments rather than by new theories. Early atomic models described matter as formed only by protons, electrons, and neutrons. But particle accelerators revealed dozens of new signatures, generating a complex framework. This new map is known as the Standard Model of Particle Physics and contains 15 types of particles and 4 fundamental forces used to build everything in the universe. And these 4 maps, which I have just presented, are accepted as the foundations of modern physics. They work very well, but they do not describe a single unified universe. And in some cases, the application of different maps to the same problem can produce incompatible results. This has led physicists to search for a complete labyrinth map, connecting all maps through new links. Einstein himself began this search for a unified theory, but it has not yet been achieved. Some physicists proposed new maps, such as string theory or quantum gravity theories. But these models rely on concepts like extra dimensions that cannot be tested experimentally. And also, physicists like Stephen Hawking argued that achieving a unified theory is impossible. They believe that these maps refer to unconnected universes, forming separate labyrinths. My view is different. For me, the universe is unique, and a unified map connects all things. This unification has not yet been achieved because of a fundamental problem that I call the YW gate problem.
The YW gate problem.
A real labyrinth with hidden rooms has doors and secret passages leading to them. In general, we can identify 3 types of doors: simple doors, Y-shaped doors, and W-shaped doors. A simple door, once opened, is a solved problem. It simply leads to a new room to be explored. A Y-shaped door leads to 2 corridors. When one corridor is opened, the other is blocked. The W-shaped door is an extension of the Y-type. Besides the 2 known side corridors, there is a third hidden corridor. Usually, to find this hidden path, we must break the door. This door classification helps us understand why modern physics is so fragmented to this day. Let us first imagine a single labyrinth with several entrances and one connected exit. This means that, starting from any entrance, it is possible to reach the exit or even another entrance. And so, we can draw a single continuous line that passes near all entrances and reaches the exit. We can call this line the labyrinth solution path. It may branch into parallel routes, but it always returns to a single path, and so at certain critical points, the path can be interrupted. If the labyrinth solution path is broken, parts of the labyrinth become isolated and unreachable. This interruption can occur when the labyrinth solution path crosses Y-shaped or W-shaped doors. An error in one Y door represents a bad choice, opening a wrong corridor and blocking the right one. An error in one W door represents a lack of knowledge. We see 2 corridors, but not the hidden path. And so, I believe that today, the maps of the universal labyrinth of physics appear disconnected, because Y doors were opened on the wrong side, and W door paths remain hidden. And as long as these wrong choices or hidden paths remain, the labyrinth cannot be unified.
Conclusion.
Today, because of these Y and W door problems, modern physics faces multiple dead ends. Its models are unlinked, and theoretical progress over the last decades has stagnated, arguing that the labyrinth is broken at its foundation and that a unified theory cannot be found. This was one of the reasons why Stephen Hawking eventually threw in the towel. I disagree with Hawking. Our universe is unique, and it can be unified using the right foundations. Throughout this series, we will show that today, nearly 50 doors were opened on the wrong side. These doors act as structural pillars of physics, but became crooked, pointing the wrong way. By opening doors in the right way, it becomes possible to link classical and quantum mechanics, the theories of relativity, and obtain a simpler model of fundamental particles and forces. Furthermore, with a unified map of the labyrinth, it becomes possible to see it in full detail, and naturally, to solve the open enigmas and explain the mysteries of modern physics. Because when the map is complete and rests on solid foundations, the mysteries cease to exist. All this will be explored in the next chapters.